Okay, let's get started reviewing your guys' test. So here's the first problem that I gave you. Two workers pull horizontally on a heavy box, meaning that they're not lifting it, but one pulls twice as hard as the other. The larger pull is directed at 25 degrees west of north, and the result of these two pulls is a total of 460 newtons directly northwards. Use vector components to find the magnitude of each of these pulls and the direction of the smaller pull. So first off, we want to set up our system. Now, just as a matter of convention and for the sake of sanity, we always call up north to the right, east, down south, and to the left, west. So please on your future tests, use that convention. Okay, anyway, so we've got this first one, which is 25 degrees west of north. So you start north and go over 25 degrees, so that's going to look something like this. So here is our F1 vector, 25 degrees. We're going to call this our F1 vector. And then our second one, however it's pulling, it's making our resultant force directly upwards. So it has to be pulling somewhere in this direction, we don't know. So here is F2. Remember, pictures can lie, but it's at some unknown angle, I'll call it theta. We know that the resultant vector of F1 and F2, when you add them together, is some vector, I'll call it just capital F, pointing straight upwards. Now, using some of our information, let's write down what we know. So first off, our resultant vector, its magnitude, is equal to 460 newtons. That's what we know. The other thing we know is that the magnitude of F1 is double that of F2. So I also know that the magnitude of F1 is equal to double the magnitude of F2. So now, putting these together, let's use Newton's equations to evaluate in the x and y direction. So let's see, in the x direction, what do we have? I know that our object is moving directly that way, so it has no net force in the x direction. Its net force is only in the y direction, or the north-south direction. And so in the x direction, I know however hard F2 is pulling it that way, F1 is pulling it with an equal and opposite force that way. So I know that the magnitude of F1 in the x direction, so F1 sub x, is equal to F2 sub x. Now rewriting those equations in terms of their angles, what do I know? Or in terms of their magnitude and their angle. So F1, how much are we going in that direction? Notice that if we were to break this into its component vectors, one going this way and one going that way, then we would be using the sine of the angle. So F1x is the same thing as F1 times sine of our angle. In this case, we know it, 25 degrees. Okay, and that has to be equal to whatever this one is. This one is going to be F2 times sine of theta, whatever theta turns out to be from this equation. So that's what we have in our x direction. In our y direction, what do we know? Well, we know that our total, our net force, has to be equal to the sum of the forces in the y direction from each of these components. So it has to be equal to F1's y component plus F2's y component. So rewriting again the same equation, we know that 460, big F, its magnitude of that F, big F, is equal to, in our y direction, what's F1 sub y in terms of the magnitude of F1 and in terms of the angle? Well, this time it's going to be the cosine of that angle. So that is going to be F1 times cosine of 25 degrees, and then plus F2 sub y, just cosine of that. So F2 times cosine of whatever our mysterious angle theta is. So that's how we have it so far. Now, we're trying to find what F1 equals the magnitude of F1 and the magnitude of F2. And then our angle theta. That's just for these. And then our angle theta. So those are the three things that we're looking for. That's a question mark now too. Okay. So we have these two equations with two unknowns. You've done this 1,000 times. You just plug in, you solve for one in terms of the other and plug it into the other. So what is, well actually I have this one. So I have three equations and three unknowns. My three unknowns being F1, F2, and theta. So I can use two of them. Well, so it's just solving a system of equations the way that we always know and love. So let's replace all my F1s with F2s, or I'll take this one and start that. So F1 is the same as 2F2. So I get 2 F2s times sine of 25 degrees is equal to F2 times sine of theta. We just got to take one and plug it into the other. So in this case, I chose to substitute that into this one and see what that gives us. So replacing the F1 there with just the two F2s. So now, sorry, that's an F2. Now, kind of nice on this one, notice that the F2s actually divide out. But if they didn't, I would then solve this for F2 and substitute into here and ultimately get theta. So you can never go wrong just solving these systems of equations, solving for one variable and plugging into the other two equations. But anyways, in this case, we're kind of lucky because the F2s cancel out on both sides. And so I'm left with 2 times the sine of 25 degrees is equal to the sine of theta. And from that, I'm going to get that, take the arc sine of both sides. And so I get that theta is equal to the arc sine of 2 times the sine of 25 degrees. And so we're going to plug that into our calculator. Sorry, left that off screen. So, plugging into our calculator, we do arc sine of 2 times the sine of 25 degrees, and we get, just writing out exactly what I see on my screen here, 57.6973. Now, obviously when we give our answer, we're going to use significant figures, but a common mistake you guys are doing is you're rounding early to the appropriate number of significant figures and then using that to plug in later. Remember, don't round your significant figures until you're giving your final answer. But if I'm going to use this theta to find F1 and F2, if I round it too early, then that introduces a rounding error that can mess up my significant figures on the other solutions that we're looking for. So that's what it is so far. I know that when I round that, since we have 3 significant figures on it, everything, then the answer is going to be 57.6 rounds that up to 7 degrees. So that's going to be our answer for the mysterious angle. Now when I write, where is F2? Notice that that gives me its direction. I say 57.7 degrees east of north. So that's what I would write down here as where it is. But now let's find F1 and F2. So pick one of our equations now that I know theta. So come back to this equation. Notice that having theta now enables me to solve for F2. Is that how I want to do it? Because the F2 is dividing out both sides. Let's just do it on this one. Maybe it would have worked, I don't know. But I'm just going to do it on this one because I can see off the bat it will for sure work. So on this one, replace my F1 with 2 F2s. So I got 460 is equal to 2 F2s times cosine of 25 degrees plus F2 times cosine of our angle theta. And our angle theta still have that stored in my calculator. I'm not going to plug in 57.7. In this case, it might still give me the correct number of significant figures, but that rounding error can sometimes change your answer slightly and make you get the problem a little bit wrong. Anyways, factor the F2 out of both those sides, and I get 460 is equal to the F2 times 2 times cosine of 25 degrees plus cosine of theta, which we know what theta is. And finally, using that equation, divide both sides by this expression, I get F2 is equal to the 460 divided by 2 times cosine of 25 degrees plus cosine theta. Not sure why I did parentheses on that. Anyways, so plug that into your calculator. So 460 divided by 2 times the cosine of 25 plus cosine of whatever our previous angle was. And it comes out to 1, let me just write it out for you exactly so that we can see the rounding afterwards. Here's exactly what my calculator is telling me, 195.994. Now in terms of 3 significant figures, obviously that's going to be 196, so our F2 here is 196 newtons. Newtons, don't forget your units. And then finally, double that for F1. Again, we could have just doubled the rounding here it would have mattered, but maybe it would have. So take that, multiply it by 2, and we get our, I'm just going to write the rounded down so you can just see it from this anyways. So just the 392 newtons. Anyways, so there is our answers for the first problem. Okay, for problem 2, we have weights are tied to each end of a 20 centimeter string. You hold, well, let's draw the picture. So 2 weights, weight 1 and weight 2. Maybe give myself more space. Weight 1, weight 2, tied to a 20 centimeter string, so that length is 0.2, and they're held some distance h above the ground. The time it takes from when I release the weight to when the first weight hits the ground is equal to the time it takes from when the first weight hits the ground to when the second weight hits the ground. So let's set up our equations of motions for each of these using this kinematic equation, one of our 4 kinematic equations. So from that, for, I'll call the bottom one y1 and this one y2. So 1 strikes the ground first, I think that's more intuitive. So the height of y1 at any time is going to be equal to its initial height, in this case h. I'm going to call the ground 0, and we're going to call up the positive y direction. So our acceleration is downwards, our movement is negative. So h plus v naught t, we don't have any initial velocity, plus 1/2 at squared, our acceleration is negative g. So that's going to be minus 1/2 g t1 squared, where t1 is the time it takes for the first object to hit the ground. Similarly, for the second object, y sub 2 is going to be equal to its initial height, which is going to be h plus 0.2, an extra 20 centimeters to its initial height. Once again, no initial velocity, and then minus 1/2 g t sub 2 squared. And then finally, the last thing that we know is that the time it takes for object 2 to hit the ground is twice as long as the time it took for object 1 to hit the ground. So once again, we have our third equation. T2 is double T1. So 3 equations, 3 unknown. Now, there's no right way to do it. Just solve and pick one, substitute into the other. You can do it however you want. It should work out. Oh, last thing we need. What's the y1 that we care about? What's the final height of object 1 that we care about? That is 0. We want to know when it hits the ground, and obviously for that as well. Okay, so now we have 3 unknowns and 3 equations. We don't know T1, we don't know T2, and we don't know h. G is a known quantity, 9.8. Anyways, so let's take this equation, and so rewriting my first equation here, I'm going to write 1/2 g t1 squared is equal to h, just moving it to the other side. Now I'm going to solve for t1 squared. T1 squared then is going to be equal to, multiply both sides by 2, brings the 1/2 over here as a 2, and then divide both sides by g. So 2h over g. So there's what t1 squared equals. You can solve that for t1 if you want, but I'm going to leave it as t2, and you'll see why here in a second. I'm going to take this equation now. So that was taking this equation right there. Taking our second equation now, and substituting this into it, I'm going to rewrite it as 0 is equal to h plus 0.2 minus 1/2 g t2 squared. Remember, T2 is this quantity, so you have to square both of those. So 2 squared is 4, T1 squared is T1 squared. Now the 4 and the 1/2 are going to turn into a 2. So this is going to be equal to h plus 0.2 minus 2g T1 squared. Now we know what T1 squared is. We have that quantity written right here. So writing that out again, I'm going to get h plus 0.2 the 2 and the 2 together are going to give me, because remember, I'm substituting that in for the T1 squared. So the 2 and the 2 together here are going to give me a minus 4. G's will go out, and I'll still have my h. So now that's going to be equal to, move all my h's to this side and keep my 0.2 over there. So I'm going to add 4 over here and then subtract 1. It's going to give me a total of 3 h's over here. And we have a 0.2 there, or in other words, h is going to be 0.2 over 3. Or in other words, it's going to be 0.06 repeating, I guess is exactly what it's going to be. Now, we want to find the value of h. Let's look at our significant figures. We have 3 significant figures, 3 significant, okay, just 3 significant figures. So 3 significant figures for everything gives me that h is going to be 0.0667, Or in other words, that would be meters, but probably the more intuitive way to write it would be 6.67 centimeters. Both answers perfectly fine. So there's our second problem. Okay, so for our third problem, we have a hunter and a 1.5 kilogram monkey. They're each 25 meters above the ground, and they're separated by 70 meters. So we've got our hunter up here in some tree, come over, and over here we got our monkey up in some tree. Now, both of them are a height of 25 meters, and they're separated by 70 meters. Now, the monkey drops from the tree, just as the hunter shoots horizontally at the monkey drops from the tree in a vain attempt to escape being hit. What must the minimum muzzle velocity of the hunter's bullet be for the hunter to hit the monkey before it reaches the ground? So we want to find the minimum value we can shoot with to ensure that we still hit the monkey. So we shoot over right at the monkey, but the monkey and our bullet are both going to fall. Now, if we don't have enough velocity, our bullet's not going to go far enough, and it's just going to hit the ground before it gets there. If we use too much velocity, if we shot at like the speed of light, we would just almost instantly hit the monkey. So we're looking for the minimum velocity, so it takes as long as it possibly could to still hit the monkey. So we want our bullet and the monkey to both strike the ground at the exact same time. In the y direction, let's do our equations of motion for both the monkey and the hunter. Probably should have left that equation up from the previous problem. X equals x naught plus v naught t plus 1/2 at squared. Probably be using that again. Let's see. So for our bullet and for our monkey here, both falling to the ground, they're going to fall in the exact same way. What's that going to look like? Their height at any time is going to equal their initial height, 25, plus their initial velocity in the y direction. They're not moving in the y direction. The hunter shot his bullet horizontally, so there's no initial velocity. And so it's actually going to be minus, since I'm going to call x, y like that, and the acceleration is down, minus 1/2 g t squared, where this t is the time that it takes them to both hit the ground. And it's also going to be the time of contact. So we can use this equation since it only has, so that gives us our equation for the height of the monkey or the bullet at any given time. We want to know when it's 0. So the specific case we care about is when y is equal to 0 now, when it hits the ground. And so now we can find the time for when it hits the ground, since there's one equation, one unknown. Move this to the other side. Maybe, I don't know, we won't do too much work out. So 1/2 gt squared then is equal to 25, which gives me multiplied by 2 divided by g, and I get that t squared is equal to 50 over g. So it's not t sub 2, t squared. Or we could have said t is just equal to the square root of that. Obviously the positive one because we're not having negative time, not moving backwards. Okay, so that gave us the t that we care about. What we wanted is what must the minimum muzzle velocity of the hunter's bullet be. So the hunter, however fast he shoots in the x direction, is the same thing as his muzzle velocity. However fast the bullet leaves the gun, that's exactly the velocity it maintains in the x direction, since there's no acceleration in the x direction. So in the x direction for our bullet, so maybe x of the bullet, because this does not apply to the monkey, it's going to be, just using this equation once again, what's our initial position in the x direction, where we're going to call that 0, 0. So here's our coordinate 0, 0. So in the x direction, the bullet starts out with an initial position of 0. Initial velocity, that's what we're looking for. So the muzzle velocity of the bullet, its initial one, so VB naught, or maybe V naught B, I think is how we typically do that. V naught for the bullet times t, whatever the t is. And then there's no acceleration in the x direction, so that term's just 0. So the x position of the bullet at any time is given just by its initial velocity in the x direction, which is the same thing as its initial velocity, times time. So for the time we care about, this will give us a displacement we care about. No, we're looking for the velocity. So then the initial velocity of the bullet that we care about is just going to be equal to the x position that we care about divided by the time that we care about. Now the x position that we care about is 70 meters. So that's just going to be 70 divided by t, where t is just this time right here. So plug that in for your calculator, do 70 divided by it, and round it to the appropriate number of significant figures, and it should come out to, we care about 2 significant figures, so it comes out to 31 meters per second. Not 30 meters per second. Some of you who got that probably got that from rounding this before you divide. Okay, so now for our next problem, problem 4. We have a mysterious rocket-propelled object with a mass of 45 kilograms. So scribble that. Mass is 45 kilograms. Is initially at rest in the middle of some horizontal, frictionless surface of an ice-covered lake. Then a force directed east with a magnitude given by this equation. So if we were to draw our picture for it, here's our object. Now remember, north is always up, so east is always to the right. So a force is going to be applied on this object this way, where the force at any given time t is equal to 116.8 times t. Newtons per second times seconds in terms of t is going to once again give you newtons. So there's our force equation for this object moving eastwards. This time it's a function of time. We're not applying a constant force. How far does the object travel in the first 5 seconds after the force is applied? So we want to find it when t is equal to 5 seconds. Then what is our position? So, since the force is constantly changing, our acceleration is constantly changing. And so we cannot use our constant acceleration kinematic equations to solve this problem. That doesn't work. But that's okay. We're going to use a more basic notion that we use to derive the kinematic equations. So first off, using Newton's law, we know that our force at any time t is equal to, our net force is just this force, so it's going to be our net force. Our net force is equal to our mass times our acceleration. Notice our acceleration also has to be some sort of function of time. It's not going to be a constant. Since the force is changing, then either the acceleration or the mass is changing. But we're assuming the mass is fixed, so the acceleration has to be changing as a function of time. And so what is our acceleration function then, as a function of time? That is just going to be equal to f of t divided by m. So that's just going to be equal to 116.8 times t divided by m. Now 116.8, that's just a constant, m's just a constant, their quotient is just a constant. I'm just going to call that a k. And I'm going to stop using this explicit function notation. So our acceleration is just going to be k times t, where k is 116.8 divided by 45, whatever it is, just a constant. But there we go. There's our acceleration as a function of time. So what is our velocity then as a function of time? How do we get a velocity from acceleration? I hear you screaming, integrate with respect to time. So integrate this with respect to time, and what are we going to get? Square it, and then bring down the 2. So we're going to get 1/2 kt squared plus some constant. We'll call it v naught, our initial velocity. It's our velocity when time is 0. V is v naught if we plug in 0 for our t. And now what's our position function? Well, once again, just integrate it with respect to time. So that's going to become a 3, and divide by it gives us 1/6 kt cubed plus v naught t plus x naught. Now, we can call our starting point here 0 in the x direction, so our x naught is going to be 0. And it already told us that it started out at rest. And so our initial velocity is 0. So our x at any time is just equal to 1/6 times k times t cubed. So for this particular time, we just need to plug that in. So 1/6 times 116.8 divided by 45 times 5 cubed, or 125. So plugging that all in, and to 3 significant figures, because even though we have 4 on that, we only have 3 on that and 3 on that. So 3 significant figures, and so it's going to come out to 54.1 meters. So 54.1 meters is our answer there. That's how far it will move in 5 seconds. Okay. For this next problem, a rock with a mass, m equal to 3 kilograms, so we know our mass, m equals 3 kilograms, falls from rest in a viscous medium. The rock is acted on by a net constant downward force of 18 newtons. That's a combination of both gravity and the buoyant force. So not quite accelerating downwards with the full 9.8 meters per second squared, but instead just 6 meters per second squared when you divide by the mass to find that acceleration downwards initially. And by a fluid, resistant force of little f is proportional now to some constant k that depends upon the fluid times the velocity. So the faster we try traveling downward through that fluid, the more the fluid pushes up on us, where v is the speed in meters per second, and k is some given quantity, k equal to 2.2. Then we're going to have to find all these things. So first let's set the problem. So here we got our ball. It's initially being pulled down. It's being pulled downwards with a constant force now, F, equal to 18 newtons. Now it's going to have a resistive force here. This one is going to be variable, little f, and it's going to be k times v. So it depends upon the velocity. So initially there is no resistive force because initially there is no velocity. So part A is find the initial acceleration. So part A, what is the acceleration when our velocity is 0? Well, maybe before we do that, let's just write out our total force equation. Our net force is the sum of all the forces, so maybe F sub total is going to be equal to, let's call downwards our positive direction and upwards our negative direction. Because when we did the derivation of these equations in class, I think that's what we used. Maybe say a little bit about these equations we have scribbled here. So we did a derivation for all these equations in class, and when we did that derivation, we assumed that downward was our positive direction and upward was our negative direction, so our acceleration is going to be some positive number. Yeah. Okay, so anyways, we're going to call this our positive y direction, just like those equations told, otherwise we'd have to flip signs. So our total force now is going to be equal to F is in the positive direction minus little f. Our resistive force, we usually like our resistive force to be in the negative direction. So our arrow is pointing in the way of motion. That's why we're calling the positive direction. Or in other words, our total force, F total, is equal to, big F is fixed at 18, and then minus k times v. Now our total force is also going to give us our mass times our acceleration at that time. That's what Newton's second law tells us. So that's the same thing as ma. Now the first thing we want for part A is to find the initial acceleration. What's the acceleration at time 0? Well, at time 0 our velocity is 0. And so at time 0 we just get m times a naught is equal to 18, because this will turn 0. Divide both sides by the mass and you get a naught. Now our mass is 3, so that gives us that our a naught then is going to be equal to 6.00 meters per second squared, just keeping track of the right number of significant figures. Okay, so there's part A. Part B, what do we have? Find the acceleration when the speed is 3 meters per second. Now, we just barely found it when our velocity was 0 meters per second. Let's find it when our velocity is 3 meters per second in magnitude. So once again, in that case, we're going to get m times a, maybe call it a1 to remind us that it's not a0. This is going to be equal to, or maybe a sub b for part B, I don't know, it doesn't matter what you use the subscript there, is equal to 18 minus, our k we know is 2.2, times our velocity that we care about is 3. And so in that case, we're going to get our acceleration there is going to be, that gives us that A for part B is going to be equal to, comes out to 3.80. 3.80 meters per second squared. So there's part B. Part C, find the speed when the acceleration is equal to 10% of whatever the initial acceleration was. So for this one, we can just use this equation again. Sorry, got distracted for a second. Oh, that really zoomed out. Trying to keep me in frame. Sorry about that. Okay. So for part C, we want to find the velocity now when we know that the acceleration. So I know my acceleration is 1/10 whatever this was. So I have mass times my acceleration is 0.1 times a naught, some fixed number, 0.1 times a naught, is going to be equal to 18 minus k times the velocity I care about for part C. So move this to this side, move this over here, and so I'm going to get that k times the velocity for part C is going to be equal to 18 minus whatever this number comes out to. I'm going to move the 0.1 out front so we don't accidentally do it wrong. So 0.1 times m times a naught, where a naught is 6. And now divide both sides by k, and that will give me my VC. So for my velocity in part C, I'm going to calculate that difference and then divide by k 2.2. And that comes out to 7.36 meters per second. Okay, so now for part D, find the terminal speed v sub t. Well, we already know how to calculate our terminal velocity here. Maybe we can remind you where terminal velocity comes from. Terminal velocity is when our net acceleration is 0. So that's when our acceleration is 0, so this side of the equation is going to be 0. So for part D, this occurs when 0 is equal to 18 minus k, sorry, that's a minus k times our terminal velocity. So then, in this case, move that to the other side, then divide by k. I get my terminal velocity is equal to 18 over k. Over here they said mg over k. Notice that we don't have quite mg over k, we have 18 over k because we have our buoyant force. This was assuming mg was our total downward force, but our total downward force in this case is not mg, it's 18 instead. But so that gives us our terminal velocity. Go ahead and plug that into your calculator, and we should get our terminal velocity is 8.18 meters per second. So this comes out to 8.18 meters per second. Okay, so that is part D. Now for part E, find the coordinate, the speed, and the acceleration 2 seconds after the motion starts. So I'm going to find the velocity, the acceleration, and the position when we plug in time equal to 2 seconds. So for all these equations, I'm just going to plug in everything we know and see what it spits out because I know what all these numbers are. There's only one gotcha, and that is the g here. The g is your downwards acceleration. In our derivation, g, our downward acceleration, our initial downward acceleration, it was in free fall, so it was just 9.8. In our specific case, our g is our a naught here, and so it's going to be 6. So you just plug into each of these equations everything you know, except for instead of g there, use 6. Outside of that, you just plug and chug, and it comes out exactly the way you expect. So I already have all those numbers written down for part E. So for part E, the y that we get, the coordinate that we get, should have been 7.78 meters. The velocity that we get should be equal to 6.29 meters per second. And then finally, the acceleration that we get, this was one that is the trickiest, even though it's the easiest to compute because it's not just simply substituting into that equation, but it still comes out to 1.38 meters per second squared. Okay, and then finally, part F. F is find the time required to reach a speed of 0.9 vt. So, using our velocity equation here, we know the velocity that we care about. Our job now is to figure out the time from that. So for part F here, the velocity I care about is going to be 0.9 times vt. So I'm looking for the time when the velocity is that. And here, this gives me my velocity as a function of time. So this is going to be equal to vt times 1 minus e to the negative k over m times t, and parentheses, and parentheses. Okay, first thing I can see I can do right out the bat is divide both sides by the terminal velocity, whatever that is. So I got 0.9 is equal to this whole thing. So we're going to get 0.9 is equal to 1 minus e to the negative k over mt. Now, I'm going to move this over here and the 0.9 over there. 1 minus the 0.9 is going to give me 0.1. So that is going to give me that e to the negative k over m times t is equal to 0.1. Take the natural log of both sides. Natural log undoes the exponential. And so I get negative k over m times t is equal to the natural log of, maybe put in parentheses, 0.1. And then finally, just solve for t now. So t is going to be equal to, move the negative sign to the other side, multiply by m divided by k, multiply by m divided by k, and then times the natural log of 0.1. And obviously the natural log of 0.1 is going to be negative, so negative times negative will be positive, which is what we expect. So plug all that in, and you finally get your time. And your time, when you plug in all those numbers, these are all known numbers. So our m is 3, our k is 2.2, natural log of 0.1 is whatever it comes out to. And so when that's all said and done, it comes out to 3.14 seconds. Okay, so there was our most time-consuming problem. Maybe E was a little bit hard, but for the most part, not too bad. Okay, now problem 6. A pump is required to lift 800 kilograms of water. Scribble down our mass really quick. 800 kilograms of water per minute from a well 14 meters deep. Maybe put H here as 14. And it's going to eject it with some velocity 18 meters per second. Let's scribble that down. Our velocity is going to be 18 meters per second. A, how much work is done per minute in lifting the water? Okay, so we've got our water, some deep well here that we've got to pump in. The water down here in the well, we know that the height of this is going to be 14 meters. So first thing we're doing is we're taking 800 kilograms of water and lifting it up 14 meters in the air. That's what part A wants us to figure out. A, what's the work? Now the work is just the integral from your starting point to your ending point, just use A and B for arbitrary points, of your force dotted with your direction, and take that integral. So in our case, this is going to be very easy. This is the integral. We'll call the bottom here 0 to the top 14 of our force. What's our force? Our force is the weight of the water that we're lifting, since we're moving it up here, so that's going to be mg, times a little dh there, I guess. This might be overkill thinking about it this way, doing the integral, but you could do it this way. But maybe go back to the most simple way we first talked about work. In its most simple form, work is just equal to force times distance. And so this is just a straightforward force, the weight of the water, times the distance you move it. Now you can calculate this integral, it's going to give you the same thing, force times, when you do this integral of dh is just h, then plug in 14 and 0, and you're going to get mg times 14, or you could have just thought about the simpler way, mg times 14. In either case, mg times 14, which is going to come out to, our mass was 800 times 9.8 times 14. Equals, now it's some number on here, 109760. The part I write for part A here, rounding that, is 101, I could write, 110000, like that, rounding it to 3 significant figures, is what it rounds to. Or joules, or I could say this many kilojoules, which is more like the types of answers you saw in the book. Okay, now for part B. How much work is done in giving the water the kinetic energy it has as it's ejected? So now it's being ejected out. How do we calculate that? Well, the work is going to be equal to the change in kinetic energy, your final kinetic energy minus your initial kinetic energy. And so how much work do we have to do to shoot 800 kilograms of water off at 18 meters per second? And so that work is going to be equal to, the final kinetic energy is going to be 1/2, remember our equation for kinetic energy is 1/2 mv squared. So it's going to be equal to 1/2 m, 800, times v squared. So 1/2 mv squared minus our initial kinetic energy, which is just 0. So 1/2 mv squared here is going to just give it to us. So 1/2 times 800 times 18 squared comes out to when we round it to the appropriate number of significant figures, it's going to be 130 kilojoules. Okay, so that was part A and part B. Just need to compare with my notes here to make sure I'm not making mistakes. Okay, so there's part B. Now part C, what must the power output of the pump be? So the pump had to first do all the work in getting the water from the bottom of the well to the top of the well, and then all the work of ejecting it out at that velocity. So C, the total amount of energy being used, the total amount of work done, is equal to the sums of these two works. Now we need to be a little bit careful because these are rounded answers. Make sure we add up our two non-rounded answers. So add up our two non-rounded answers. Whatever it comes out to is the work. But we're looking for the power. So maybe remind ourselves of our power. Power is equal to our work over the time that we care about. We want our time to be in seconds and our work in terms of joules. So the work here is going to be the sum of these two works, the work from part A plus the work from part B, divided by our time here is going to be 60 seconds, because it was per minute. So now this will get it to joules per second, because in each of these parts we were calculating the amount of work done over a minute. Pump is required to lift this per minute. So this is how much energy was taken in 1 minute to lift the water up. This is how much energy was taken in 1 minute shooting it out with that velocity. So now we need to get the work per second, which is joules. So take the sum of those two, whatever it comes out to, divide it by 60, and that is going to give us it in terms of watts. Remember to round to three significant figures, and it comes out to 399. Sorry, also check with my answer. Yes. So this comes out to 3990 watts. That W now is the unit watts, joules per second, not work. Okay, now for the extra credit problem. So the extra credit problem, it's essentially trying to calculate the kinetic energy inside of a spring as it oscillates back and forth. So if I take the spring, L naught is its uncompressed length. So when it's at rest, it's at L naught, I take it and I stretch it some distance L and let it go, then it's going to oscillate back and forth, and so some energy goes into moving that spring. The crux of this problem is all about calculating the kinetic energy of a spring. So let's read it now. We usually ignore the kinetic energy of moving coils of a spring, but let's try to get a reasonable approximation to this. Consider a spring of mass n. So we know the mass of the entire spring is big N. Equilibrium length, L naught. So that's when it's completely unstretched, we're not pulling it. So as I have it drawn here, there must be something pulling it out if it's stationary there. Some equilibrium length L naught, and spring constant K. So we know whatever our spring constant is. That's some given quantity. The work done to stretch or compress the spring by a distance L is given by that equation. That's something that we already derived. The work you have to do on the spring, maybe scribble that down here, is equal to 1/2 kx squared. They're going to use a big X there, where big X is how much it's stretched or compressed. So in the particular case we have drawn here, it's always the length you have it at minus the L naught. So in our particular case, that's going to be equal to 1/2 k times L minus L naught squared. So 1/2 kx squared, where x is equal to L minus L naught. Consider a spring, as described above, that has one end fixed, that's how I have it drawn in this picture, and the other end moving with some speed v. So now we know that this end, however it's moving, so we have this oscillating back and forth, maybe going that way, maybe going that way, we don't know, but this is going to be moving with some speed v. Maybe we'll pretend it's moving that way at some speed v. Some speed v. Assume that the speed of a point along the length of the spring varies linearly with the distance L from the fixed end. So I know that the end of the spring is moving with some velocity v, but notice that this end of the spring isn't moving at all. When it says it varies linearly, that means exactly in the middle of the spring, it's moving at exactly half the speed. So this piece of the spring, as it's coiling back in, is moving the fastest, a little slower, a little slower, a little slower, a little slower, until we get all the way to this end, not moving. So the atom right next to that one is barely moving a teeny bit. So the velocity at any given point here is proportional to how far along the spring you are. So maybe, just writing that as a point, the velocity at some point then is going to be equal to how far along the spring you are, little l, divided by big L, the total length, times v. So in other words, if you're little l is how far along the spring our point is. If it's right here at 0, then we have no velocity. If it's right here at big L, so if little l is big L, then that's 1, and then the velocity at this point is going to be then just v, which is what this is saying. And if little l is 1/2 big L, 1/2, then just to show you the middle point, at the middle point, that's where little l is equal to 1/2 big L, all over big L. Cancel those out, and it gives us 1/2 v, so the middle point is moving with half the velocity. So hopefully that's making sense, what it was saying there, where we're saying that we assume that the speed of points along the length of the spring varies linearly with the distance little l. Hopefully that piece makes sense. Okay, we're also going to assume that the mass is uniformly distributed along this spring. So now what's part A and the whole crux of the problem, we're going to calculate the kinetic energy of this spring. So I need to calculate the kinetic energy of all these individual points. So I'm going to do an infinite sum here, or in other words, an integral, along the spring, so from our starting point 0 all the way to big L. And I need to take like a little slice of the spring here, an infinitesimally small slice of that, and talk about what is its kinetic energy. Well, we know the kinetic energy of that atom right there, or that little teeny slice of the spring right there. That is going to be 1/2 its teeny tiny infinitesimally small mass, dm, times the velocity at that point squared. So let's write this out again. This is equal to the integral from 0 to big L of 1/2. What is our velocity at each point in terms of L? That is just going to be little l over big L times whatever the v is of our ending point squared. And then don't forget our dm here. We'll have more to say about this dm in a second, but let's just really quick mess with all this and understand what here is constants and what's not. So for each atom along this thing, 1/2 doesn't change, big L doesn't change, and the velocity of the endpoint doesn't change. Only that little l changes. So just trying to make really clear what changes as we're integrating for each point here and what's just constant. So we can pull the 1/2 out front. We can pull that L out, but remember that's an L squared. And we can pull the V out, but that's also a V squared. So times V squared over big L squared. Inside here, we still have that little L squared. And we have times Vm. Okay. Now, we can't just integrate this because this is doing it in terms of mass, but we want to integrate along a length. We need to rewrite our mass in terms of our length somehow. Now, the last thing that we knew is that the mass was uniformly distributed across this. And so, what that means is half the spring has to have half that mass. A fourth the spring has to have a fourth of that mass. So now the mass of just a little teeny part of the spring is going to be equal to a teeny tiny part of the length times whatever our big mass was. Oh, sorry, not times our big mass. Times our big mass over our length. Okay, there we go. Maybe here's a better way to have thought about that. The density, mass over length, has to be the same for this whole thing. So the mass over the length of the entire spring has to be equal to an infinitesimal little bit of its mass over an infinitesimal bit of its length. Not sure if that's a better way to help you think about it. You can think about this as giving us the density per meter. Maybe that's a better way to think about it. So M over L is telling us kilograms per meter. And so how much mass is in some small portion? We take the length of that portion and we multiply it by however many kilograms per meter we have. And that gives us our mass for that portion. So trying to come at this in a couple different ways, but in essence, we can make this substitution dm for dl times big M over big L. So this is now going to be equal to, once again, we still have our 1/2 v squared over L squared times the integral from 0 to big L of L squared, but now make the substitution. So times dl times big M over L. Once again, those are constants, so let's bring them out here as well. So we're going to get 1/2 times v squared times big M all over L cubed. That was bringing those out. Now we can do our integral from 0 to big L of L squared times dl. That's our only variable where we are, L, along this. So L in our case, when we're doing this little segment, is this distance right here. So we're integrating as L goes all the way across this, calculating the kinetic energy of each little piece of the string, doing that for all infinitely many from 0 to big L, however far over we are. Calculate our integral here, and what do we get? We get 1/2 v squared times M over L cubed, just our constant, times what we get when we evaluate this integral. Make that cubed and bring out the 1/3, so 1/3 times L cubed, but L we're going to plug in big L and then minus 0. So we're just going to plug in the big L result. Okay, now what do we notice? The big L's cancel out with those big L's. 1/3 and 1/2 is 1/6. 1/6, we still have our M, and we still have our V squared. So the kinetic energy for our spring is going to be 1/6 mv squared instead of 1/2 mv squared, which would have been just for some point at the end there. So there is the heart of the problem, part A. So part A, our equation is that the kinetic energy of the spring is equal to 1/6 times its mass times v squared, where v now is the velocity of whatever that M point is. Okay, so now they gave us a bunch of information that we know. Let's see. Hint, starting here. Okay, in a spring gun, a spring of mass, so we have some given mass for our spring, that's our big M. So now in this concrete case, maybe we can afford to erase a little bit over here. So now in this concrete case, we know what our K is. We know what our big M is, the mass of the spring. That is equal to 0.243. So there's the mass of our spring. And a force constant, so there's our K. Our K is equal to 3200. Is compressed 2.5 centimeters. So our big X was our distance from here to here. We know that's 2.5 centimeters. I'm going to keep everything just in terms of our standard units so that we don't get confused. So I'm just going to write that as 0.025 for 2.5 centimeters. Just read this again. Starting right here. In a spring gun, a spring with that mass and a force constant of that is compressed 2.5 centimeters from its unstretched length. When a trigger is pulled, the spring pushes horizontally on some ball, so we'll use little m for the mass of our ball. That one's mass is going to be 0.053 kilograms. We won't bother with that, standard units. The work done by friction is negligible, so we can ignore all friction. So assume all the stored up energy in the spring goes into the kinetic energy of the spring or the ball. Calculate the ball speed when the spring reaches its uncompressed length, ignoring the mass of the spring and then including the mass of the spring. So we compress our springs and then we release it to shoot the ball out. And we want to know how fast the ball is going when the spring reaches its uncompressed length. So the work that the spring does has to be equal to our change in kinetic energy. So the change in the kinetic energy of the ball, and we don't have the kinetic energy of the spring right now. So what is the work done? The work the spring does is just equal to 1/2 kx squared, where we know all those quantities. That has to be equal to the kinetic energy of the ball, which is going to be equal to 1/2 little m for our kinetic energy of the ball times v squared. We were looking for that v squared, if I remember right. Calculate the ball speed. Okay, so we're looking for whatever that v is from this equation. Multiply both sides by 2 to get rid of the 1/2. And so V squared is equal to K over M times X squared. Or in other words, V is going to be equal to, obviously, the positive answer, since we're talking about just a speed, a magnitude, the square root of K over M times X squared. Now you plug that into your calculator. All those are known quantities. That's right there. M is right here. K is right there. Plugging that into your calculator, you should get that this is equal to 6.14 meters per second. Okay, part C says, now this time include the mass of the spring as well. So some of the kinetic energy that comes from this work is going to go into pushing the ball, but some is going to get absorbed by the spring moving. So now let's do it again, but this time work is going to be equal to the kinetic energy of the ball plus the kinetic energy of the spring. And so now this is going to give me work, once again it's the same work, so 1/2 kx squared is equal to kinetic energy of the ball, that's still the same thing, 1/2 mv squared plus the kinetic energy of the spring, which is going to be 1/2 big M, to remind us that's the mass of the spring, not the ball, times v squared. We're assuming that the end of the spring and the ball are moving at the same speed when the spring is uncompressed. Okay, so now we're going to be solving for v from this. Once again, multiply both sides by 2, which gets rid of that, that, and that. Factor the v squared out of this side, and so I'm going to get, rewriting this equation up here, kx squared is equal to, factor the v squared out of those, so we're going to get v squared times m plus big M. And so now v is going to be equal to k times x squared over m plus big M, all under the radical. So notice that the only difference there is you do little m plus big M on that. No, we did something wrong. Shouldn't be that. Oh, I know what I did wrong. Obviously, 1/6, not 1/2. So this should have been a 1/6. Sorry about that. Okay, so multiplying everything by 2 still left us a 1/3 on that. So this is going to be plus 1/3 big M. Okay, now still solving for the velocity here, so same as before. So not that different, but did have that mistake. So this is equal to the square root of k times x squared all over m plus 1/3 big M. Okay, so rather than it being just the m in the denominator, it's the little m plus 1/3 the big M. And now when you multiply that all out, you should get 3.86 meters per second. So 3.86 meters per second, and it better be smaller. So before, this is what we had, not counting the mass of the spring. Here's what we had counting the mass of the spring. So we see some of the energy had to go into moving the spring, and so the ball's moving slower in that case. And then finally, in part C, what was the final kinetic energy of the ball and of the spring? So that's just plugging back in to these equations right here, or plugging in this and this. So 1/2 mv squared using that velocity, and 1/6 mv squared using that velocity. On this one, you use little m, and on this one, you use big M. And so if you just plug in, you should get that the kinetic energy of the ball is equal to 0.396 joules, and you should get that the kinetic energy of the spring is equal to 0.604 joules. Now, the sum of those two kinetic energies better be equal to this work that we did. You'll notice when you plug this in, the work that we did is just 1/2 kx squared. They gave us this so that it comes out to exactly 1. So this will come out to exactly 1, so the sum of these two better be 1. Okay, so that's the extra credit problem, and that's your whole test.